Hello everyone. Today we are diving into the core of motor control, building a switching logic controller for a BLDC DC motor using MATLAB and Simulink. We will be focusing on how to sense the rotor position and translate that into a precise switching pulses. Let's start with the big picture. Here is our full model, and we have BLDC motor block at center, powered by three-phase inverter. And to get this motor spinning, we need a closed loop control that knows exactly where rotor is at any given moment to trigger the right gate pulses. So first we'll be putting up the sensor. So in sensor, we'll be using these blocks which I'm using, and I'm taking as a theta as an input. Since the rotor spins continuously, the angle value keeps on increasing. We use a math function block set as reminder with a constant of 360 degree. This ensures our signal always stays within 0 to 360 degree. Then building a sector logic. So now we are building the sector logic. So a 360 degree full circle can be divided into 6 sectors. From 0 to 60 degrees first sector. We are using relational operator and AND gates to define these boundaries. For example, sector 1 is active when theta is between 0 to 60 degrees. We convert these logic results into a data type the rest of our model can read, and that data type will be using inherent. We'll be putting here inherent. So once we know the sector, we need a switching pattern. So before that, we'll be doing this thing repeatedly for our 6 sectors. So this is a pole pair. So now sector number 2, which is starting from 60 degree to 120 degree. So I'll be putting this sector image for reference. So you can see that. So I'll be putting here 60, then 120 degree, then repeating this for complete 6 times for representing the 6 sectors. So here you can see that these are the all the 6 sectors: 180 to 240 degree, 240 to 300, and 300 to 360. So that's why we have rounded off or limited our theta to between 0 to 360 degree. So once we are done with this model, what we'll be doing is we'll be making a subsystem. So how we can make subsystem is by selecting the complete this all the 6 sector what model we have made. So now we are done with the sector, all the 6 sectors. So our this particular part of model can detect which sector we are in. So this is sector number 1. Whenever the theta is between 0 to 6 degree, we will be having sector 1, then sector 2, then sector 3, and so on and so forth till sector number 6. So I'll be putting a number to every input. So we will be adding all the inputs coming from the sector block, sector identification block, we can say to this, or simply a sensor block. So I'm making it into a subsystem, and subsystem name I'll be putting as simple sensor. So this block becomes our core identification block, which identifies our sectors, or simple a sensor block. In real BLDC motors, this work is done by a Hall sensor which detects what is the position of our rotor. So now inside the switching block, what we'll be doing here is, now I'll be putting 6 switching patterns for 6 sectors. So here is our switching pattern. So first switching pattern is A high and C low, which we have earlier used in our previous videos. So now I'll be putting all kind of pattern which are useful in that particular sector. So for sector 1, sector 2, sector 3, and likewise I'll be. So once we are done with the switching pattern, now we'll be using a multi-port switch. So let me finish with the switching pattern. This is sector number 5. After this, I'll be going with sector number 6, and this is our last sector, which represent theta between 300 degree to 360 degree. So now we are done with our complete switching. Now this is a simple switch or 2-port switch. I need a multi-port switch. So here is a multi-port switch. So I'll be using multi-port switch, and how many sector we have? 6. So I'll be using 6 number here. So I'll be connecting it. We can directly connect it by selecting the input and output and pressing the control button. So you can do that. But now what I'll be doing is I'll putting a feedback. Feedback is coming from our sensor, and these 6 input I can use here. Now what I can do here is I can convert this into a subsystem. So the switch which we are using, a multi-port switch, it will select sector 1 if our sensor output is 1. It will select sensor 2, 3, 4, 5 and 2, 6 if our sensor output is between 1 to or 6. Whatever the sensor output is, accordingly it will select the switching pattern, and that switching pattern we will be giving directly to our inverter, which is 3-phase inverter. So now if everything is done, we have put a feedback to. So now it's time to run the program or simulation, but as every engineer knows, it rarely works perfectly first time. So what we'll be doing is there is a problem of relational operator overlapping boundaries. So we'll be fixing this. So which is causing the model to think in 2 sector at once. So let's go back and into the sector and refine those things. So now again, when we are running it, we can see that theta is coming 0 degrees. So what is the problem here is that the angle which we are seeing, which the sensor is sensing, is also coming negative. So what we want is, we want a positive angle. So what we'll be doing is, we will be using a magnitude operator, or we need only the magnitude part of the theta. So I'll be putting this, and inside what we'll be doing is, we'll be adding a additional angle, so that whenever the angle is between 0 to 60 degrees, say 40 degrees, so the commutation should be forward by 30 degrees. So this is done to avoid rotor to stuck at some place. So we'll be again running it. So now with the fixed logic, the simulation run smoothly, and on the scope you can see motor speed ramping up, and also the rotor rotating. The animation we have built in previous video, we are using the same animation. So now I am changing some inertia to have a more smoother operation of rotor. So again I will be rotating, and now we can see that the rotor is rotating smoothly. So this, and also the speed, you can also see the speed is coming perfectly fine. There are some torque ripple which is natural in BLDC motors, and here is a theta, and these are the switching patterns. So switching patterns, you can see sector 1, 2, 3, 4, 6, and then coming back to 0 or 1. Then again going back to 1, 2, 3, 4, 6, and animation you can see that it is perfectly working. The switching is also happening. The color red and blue are showing the switching on A, B, C phases. So this is all you have. The functional BLDC switching controller built from scratch. And if you found this helpful, do subscribe to our channel for more such videos. Thank you.